In this video, we're going to take a look at one example in which the underlying distribution of a random variable is not normal. In fact, it's exponential. Let's read it. It says the life length of an electronic component, and that is a t because it's a random variable, is, we call it t, is exponentially distributed with a mean of 10,000 hours. So t is a random variable that is not normal. In fact, it's exponential, follows exponential distribution with parameter lambda. Okay? And just to remind you of what we talked about earlier is that when an underlying population is not normally distributed, which is the case in that problem, the sampling distribution will be normal if the sample size is sufficiently large. The sampling distribution of the mean will be normal if the sample size is sufficiently large. So in this example, it tells us what is the mean of t. And when t is an exponential random variable, we know that expected value of exponential is 1 over lambda. In fact, standard deviation and expected value of exponential random variable are both equal to 1 over lambda. That is a property of exponential distribution. And in fact, that is equal to 10,000. That means lambda is equal to 1 over 10,000. What is lambda? That is the rate, if you remember from Poisson process when we talked about exponential random variable. Lambda is the rate. Basically means per hour 1 over 10,000 electronic components fail, or their life ends. So in part A, it's asking what is the probability that a single component lasts more than 9,500 hours. A single component. A single component's life is t. So in part A, what is basically asked here is that what is the probability that t is greater than 9,500? Well, we know that t follows an exponential distribution. And in order to calculate that, we change this to CDF, 1 minus probability of t less than 9,500. And this is the CDF of exponential. And we know that CDF of exponential, what is the formula for that? So 1 minus, the CDF is 1 minus e to negative lambda t, right? So, and in this case, will be basically equal to e to negative lambda t, which is equal to e to negative 9,500 divided by 10,000. That is lambda times the t. So, and then you calculate that, you'll get 0.39. So 39% chance that the life of this component lasts more than 9,500 hours. That was nothing new about, and we already knew how to calculate that from the previous modules. But in part B, it says, utilize the central limit theorem to approximate the probability that the average life of 200 components is more than 9,500 hours. So now we're talking about average life of 200 components. So right here, the 200 is your sample size. Now our new random variable is x bar 200, which is the average of 200 components. And we know that this is going to be a normal random variable, but this normal random variable will have a mu and a sigma that we need. The mu is going to be the same mu, that is 10,000. Sigma will be sigma over square root of n. That's what we learned in central limit theorem. The new sigma. So basically, let's call it sigma of x bar will be sigma of t divided by square root of n. Sigma of t is 10,000, as we talked about here. And for exponential, sigma and expected value or average are both the same, that is 10,000. Divided by square root of n, which is the square root of 200. And that is equal to 707.106. So now we know the new mu and the standard deviation of this normal random variable, which is average of 200 components. Now we want to calculate probability that x bar 200 is greater than 9,500 hours. That is equal to 1 minus probability of x bar 200 less than 9,500. And because x bar 200 is normal, what we need to do is to convert this to a standard normal, probability of z less than 9,500 minus 10,000 divided by 707.106. And that is equal to 1 minus probability of z less than negative 0.707. And you read that from the table, and that is equal to 76%. So there's 76% chance that probability of their life is more than 9,500 hours for 200 average of 200 components.